Okay. All right, so I'll start by briefly introducing Flow, and then I'll introduce our speaker. So Flow is a seminar series on federated learning, broadly construed, and we host speakers on a wide range of topics such as ML, distributed optimization, privacy, or even cryptography. So if you have any suggestions for speakers, please feel free to get in touch with us. Two quick admin things. This talk is being recorded. And if you have questions during the talk, as Samuel just mentioned, please write them into the chat or raise your hand in the Q&A. So that being said, it's really my pleasure to introduce Gauri Joshi, who has been an assistant professor at CMU since the fall of 2017. She got her PhD at MIT, and her research is at the intersection of computer science, machine learning, but also electrical engineering. And she has gotten a number of very significant awards, notably recently an NSF Career Award in 2021, an IBM Faculty Award in 2019, but also the Best Paper Award at ACM Sigmetrics. So today, Gauri will talk about how to handle heterogeneity in large-scale distributed learning systems, and I'm really looking forward to her talk.
Thank you, Dan, for the great introduction, and thanks for the invitation to this seminar series. It's my pleasure to present this work on tackling computational heterogeneity in federated learning. This is joint work which is led by my students Jianyu Wang and Yeji Cho, and we have collaborated with several folks over the years at Princeton and Google. Also, some master's students at CMU have been involved in these projects. With that, acknowledgement to the people who did the real work for the talk that I'm going to present today. Let me introduce the high-level goal of this talk. So, as all of you know, federated learning is this emerging machine learning paradigm to run distributed training on resource-constrained edge devices like mobile phones, IoT devices, etc. And heterogeneity, both in terms of data as well as the computational capabilities of these devices, is a major challenge in federated learning. So in this talk, I'm going to talk about two works that focus on computational heterogeneity, first in terms of devices having different computation speeds or using different local optimizers. And secondly, in terms of intermittent availability of the devices, which means that in every training round, only a subset of the client devices participate in training. So we'll try to understand what effect that has on the convergence and the consistency of the solution, and how do you fix inconsistency problems if there are any. So since this is the Flow seminar, I guess I don't have to give too much of an introduction on federated learning, but I'll do that just in a few minutes to introduce the notation that will be used in this talk, and I'll go to the details of the work very soon. So when I mean federated learning or training, it is synonymous to running distributed SGD or stochastic gradient descent, because it's the most commonly used algorithm to optimize objective functions in machine learning. So in machine learning, the objective function takes this form of the empirical risk function. And in order to minimize this empirical risk function, we typically perform mini batch SGD, where we start with some version of the model. So this vector X denotes the weights and the biases of the model that you're training. It's the parameter vector. And starting from this parameter vector, in every iteration, we compute gradients over a batch of B samples that are chosen from the training data set. And we move along the direction of the stochastic gradient that's computed on those B samples. So this is an iterative algorithm that will eventually converge to the minimum or a stationary point of this objective function f of x. Now, although this is an inherently sequential algorithm, for large data sets, it is too expensive to run it on a single server. So in most practical implementations, we parallelize this algorithm by dividing the training data set into multiple worker nodes. So this is what is done in most implementation. It's called distributed SGD or synchronous SGD in the data center setting. So in the data center setting, we take the training data set, we shuffle it, and then evenly partition it across some M worker nodes. These are servers in the cloud, and each of them stores a portion of the data set. And then there is a central server, often called the parameter server, which aggregates the gradients or the model updates that are sent by these workers. So the standard synchronous SGD implementation is that these workers will read the current version of the model from the parameter server. Then they will compute gradients on one mini batch of data from their local data set. And then the parameter server will receive all these gradients, average them, and apply the update rule that we saw previously. So this is synchronous SGD. Now, if we think about the scalability of this framework, that is what happens if the number of workers M increases, then there are several challenges because some of these workers may slow down. So there can be straggling issues. They may have different computational speeds. Also, the communication on this link between the parameter server and the workers can be slow. So these practical or system level issues affect and limit the scalability of this parameter server framework. So over the years, several works have been proposed which change the aggregation mechanism of distributed SGD in order to improve the scalability of this framework, including some of the works from my group, such as asynchronous SGD, on local update SGD, on overlapping communication, computation, etc. So there's been a long line of works on this. I'm not going to go into that in this talk, but I want to highlight that these issues, because they also occur in federated learning and are in fact magnified because of the scale of the system and the resource constraints. So some of the limitations of this parameter server framework are that it generally assumes that the workers are homogeneous and available throughout the training process. And more importantly, it considers that there is a centrally available data set which can be shuffled and evenly partitioned across the worker nodes. But these assumptions, especially the second assumption, breaks down in many modern applications where data is being collected at edge devices like cell phones. So an example application of this is the next word prediction service, where when users type anything on their cell phones, there is a service that predicts the next word. So here, what the user types becomes the training data. And these training data can be used to train informative models that can predict the next word accurately. And this is just one application. In general, there are massive amounts of training data that are being collected at edge devices that can be used for data-driven decision-making. But sending these data directly over to the cloud for centralized training can be too expensive and slow, because the devices also have limited bandwidth on the communication links that connect them to the cloud. And moreover, there are also privacy laws that forbid data sharing with foreign servers. And if these devices are geo-distributed across the world, then privacy laws are different in each country, and it can be an issue to share data with a foreign server. So In order to get around these communication and privacy constraints, a framework called federated learning emerged in the last few years. The core idea of federated learning is that the data stays on the device, whereas the model training is shifted over to the edge. So in each round of federated learning, the edge clients will read the current version of the model from a central aggregating server, and they will do several local updates to the model. And then these resulting models are averaged by the central server. So the main thing to note here is that the communication that happens on these links does not transfer the data. It only shares the model. And because of that, it is much more efficient than doing centralized or data center based training. And because you're only sharing models, it provides better privacy guarantees than sharing the data directly to the cloud. So at first glance, if we look at this figure, it seems like this is just a generalization of data center based training because there's a central server and there are these worker nodes, which now are the mobile clients. But there are several key differences which set this federated learning framework apart from data center based training. The first main difference is that the data are highly heterogeneous across devices, both in size as well as composition. And this is because the data is collected by the devices rather than being partitioned by a central server and allocated to the devices. So data heterogeneity is a major issue that has received a lot of attention in the last few years in federated learning literature. But another issue, which is going to be the primary focus of this talk, is computation speeds, which can be varying across these client nodes. So the client nodes can be of different types. Maybe some of them are cell phones, some of them are tablets, etc. So it's not just short-term fluctuations in speeds as they occur in the data center setting, but here the computation speeds can be consistently and arbitrarily different across the client devices. So we will see how this can affect the quality of the solution and the training algorithm. Besides computation heterogeneity, there's, of course, communication limitations, which was the motivation behind federated learning. And because of the communication limitations, these clients perform multiple local updates to the model rather than just computing gradients and sending them to the central server. And another thing that's different here is that the sheer scale of the system is an order of magnitude larger than the data center setting. So in the data center setting, maybe you have tens or hundreds of parallel workers, but here we could have thousands or even millions of these geo-distributed devices. And as a consequence of this large scale of the system, only a subset of the devices are available for training at a given time. So this can also pose some challenges to the convergence and the stability of algorithms. Because devices are only intermittently available, often when they are just plugged in for charging. So only for a short period of time, they can be used for training, and only a small fraction of them can be used for training at any given time. All right, so these are the main differences between data center-based training and federated training. Now let me define more concretely the federated optimization objective function that we are going to use throughout this talk. So as most of you might know already, if you work on federated learning, because these clients have different data sets, we define something called the local objective function, which is just the empirical risk computed over each client's local data samples. And then the global objective function, f of x, is a weighted average of these local objectives. And the weighted average is taken with the weight set to be proportional to the size of the data set at the ith client. So this pi is equal to the fraction of data that is there at the ith client. The reason why we choose pi as this is because we want to emulate centralized training as if we had all the data available in a single location. So that's why pi is set to the fraction of the data size. Now you can see from these definitions that the local and global objectives can be very different depending upon these data sets di. But our objective is to find a single global model that minimizes the global objective, which is this weighted average. So that's the goal that we are going to work with. Note that there are several works that consider variants of this goal, where you train personalized models or you train more fair models. And to do that, you have to modify this objective function. But we are going to go with the standard global objective function where we want to train a single global model. Okay. So this is the objective function, and the standard federated averaging algorithm is operating in terms of communication rounds. So in each communication round, the current model is sent to the set of chosen and available clients. And then these clients do some tau local SGD steps using their own local data set. So after these tau local SGD steps, because of the data heterogeneity, the clients will end up with different versions of the model. And then these updated models are aggregated by the central server in proportion of the data set fraction pi. So this is the standard algorithm. And what we want to understand is how does this work in the presence of data and computational heterogeneity? So now that we have set the stage, the outline for the rest of the talk is that we are going to consider three different aspects of this system. The first will be about data heterogeneity. So I'm going to talk about this only briefly. And the focus here is to understand how the choice of tau will affect the conversions. So this is a work that was presented a couple of years ago in MLSys. It was actually in the context of distributed training, but it can be also applied in federated learning. And then I will talk about computational heterogeneity due to different client speeds, as well as due to intermittent client availability. So are there any quick questions at this point? I can take questions if there are any.
I don't see any question in the chat, so if you have any quick question, please post it to the chat or just raise your hand. Maybe we can wait like 20 seconds. Somebody has a question.
Okay, so it seems like there are no questions.
Everything clear so far.
All right, then I'll move on. So let's try to understand how the number of local updates tau affects the conversions as well as the communication efficiency of this federated training algorithm. So the first thing, which is very easy to see, is that as we increase tau, we perform more local computation and less frequent communication. So having a larger tau is very good in terms of communication efficiency because you will end up doing more iterations within the same number of rounds if you have a larger value of tau. But on the other hand, let's see how tau affects the quality of the final solution. Although it gives faster convergence in the sense that we do more iterations per communication round, the quality of the solution might be affected adversely by tau. So to understand that, I'm going to consider a toy example and show you two extreme cases. One is where tau is just equal to 1. So this is a toy example where you have two clients where their local minima are x1 star and x2 star. And x star is the global minimum that we want to reach. So if this is the current version of the model that we start with, and if each client does one local update, then their model will move towards their local minima. And then after averaging, we get this updated model. And if we repeat this process, then we will see that this path taken by the global model eventually goes towards the global optima. And if we choose the learning rate carefully, then we can in fact show that this will converge to the global optimum or the global stationary point. So with tau equal to 1, this is just equivalent to doing synchronous SGD. So the convergence guarantees that we have for synchronous SGD or mini batch SGD carry forward to this setting. But if we go to the other extreme where tau is large, then let's see what happens. So if starting from the global model, if each client does many local updates, then their local model will reach close to their own local minimum, which is x1 star and x2 star in this case. And once we average these models, we will get a global model like this. So from the picture, it might seem like we are making swift progress towards the global optimum. In just one communication round, we moved quite a bit of distance here. But it turns out that it can get stuck at this point, because after this communication round, if we do another communication round, then starting from this global model, these clients will again do many local updates, and they will go towards their own local optimum again. And when we average, we are back at this point. So the problem here is that what we are getting is an average of the local optimum, which may not match with the global optimum because the objective function is a nonlinear function. So this picture, I hope it clarifies that a large tau can result in an inconsistent solution which differs from the true global optimum. So more formally, we can actually analyze the convergence in terms of tau, and we can show that after T communication rounds, the error can be bounded, something like this, where there are two terms. The first term decreases with tau because here, as you increase tau, you do more iterations in the same number of communication rounds. Whereas the second term, it increases with tau. This corresponds to the inconsistency that is coming in because of the local optima being different from the global optima. And this term also increases with the amount of data heterogeneity, which is captured by this parameter kappa. So you can see that it increases with the order of kappa squared. So this bound is not the tightest that is available in the literature, but the general trend holds true for all the convergence analysis that have been done here, where one term decreases with tau, where another term increases with tau. So if we look at the convergence in terms of the training loss versus the number of communication rounds, this is the kind of trade-off that we get. So initially, we can see that actually large tau is really good. But as you come towards the end of the training process, then a smaller tau is better because it gives more consistent solutions. So in order to operate at the best sweet spot between these two extremes, there have been several solutions that have been proposed in recent literature. So many of the solutions propose setting a small enough value of tau or choosing a small enough learning rate such that this divergence between the local models is minimized. There's also some proximal methods that pull back the client models towards the global model. There are several variants of these proximal methods. So as an alternative to this, what we propose is an adaptive strategy that decays tau as we go through training. So at the beginning of training, we propose using a large value of tau, but as you come towards the end of training, you reduce it to a smaller value of tau. So this is in the case of a fixed learning rate. If the learning rate is varying according to a schedule, then this adaptive strategy can also be modified accordingly to account for the variable learning rate in the schedule for tau. So the way we get the schedule for tau is that we optimize this error bound with respect to tau and determine at every time what is the best tau that we should choose. So this was my quick overview of data heterogeneity and the choice of tau. Now, next I will move on to computational heterogeneity, which I'm going to spend more time on in the rest of the talk. Are there any questions again?
We have one raised hand.
Mm-hmm.
Let me just try to unmute Konstantin.
Thank you. Can we back to the previous slide?
Sure.
And can you just do two questions? Can you comment on some or all of these parameters? And also, I don't see any like neighborhood. For example, in the previous example, you showed a counterexample where we just stuck and we don't even reduce the true error. So in that example, as t increasing, the bound vanishes. And so can you comment on this, please?
I think the audio is not clear, so I was only able to partially hear your question. But I think you're asking about like, why is there no inconsistency here? So earlier I showed that with large tau that it can converge to a bad solution.
Yeah. Yes, exactly.
Yeah, so here, if tau is small enough, so this bound is for some small enough tau, we don't let it to be arbitrarily large. And if tau is small enough, then we can show that you get convergence like this. And the inconsistency is captured in this term. So this term, because we are decaying the learning rate, it is decaying with t, but if we keep a fixed learning rate, then you will actually have a constant error floor over here. So I hope that answers the question.
Okay, I mean, so is this bound also covers previous case when we really does not converge to optimal solution? Or this bound is
oh, I see. So okay, this is about convergence to stationary points for non-convex objective functions.
Okay, got it. Thank you.
Right.
Okay, and then we have two clarification questions in the chat, so maybe I can just read them out loud for you.
Sure.
So the first one by Trapti is, what do you mean by handling heterogeneous client architectures?
Handling heterogeneous client speeds, you mean? I did not say architecture.
Yeah, the question says architectures, but I would guess that it means.
Oh, okay. If you're asking about computational heterogeneity, then I will clarify that in the next slide when I talk about this.
And then the second question in the chat is, how is kappa calculated?
Okay. So kappa depends on the difference between the local gradients computed on the local objectives and the global objectives. So the exact expression of kappa can be found in our paper. I can refer you to it. So it's actually in this paper. I have a link to that at the end of the talk. So feel free to look at that if you want to find the exact definition of kappa.
Yeah. So there are no other questions. Thank you.
Okay, thank you. Thank you for the questions. So let me now explain what I mean by computational heterogeneity. When I told you about the federated averaging algorithm at the beginning, I said that each client does the same number of local updates, which is tau. But in practice, in many federated learning implementations, the way it is implemented is that each client does the same number of local epochs, not the same number of local updates. And epochs means the number of traversals of the local data set. So because the local data sets have different sizes, this means that clients which have more data will do more local steps. So the number of local steps is proportional to the size of the local data sets, as we have shown here. And clients which have less data will do more local steps. So many implementations actually use this framework rather than the algorithm that I showed earlier. So this is one source of heterogeneity. Another way of implementing the federated averaging algorithm, which has been proposed in some of the works, is aimed to handle straggling clients, where instead of fixing the number of local updates that each client does, we can fix a time window and let faster clients do more local updates and slower clients do less local updates within that time because of their heterogeneous speeds, and then just aggregate the resulting updates. So this is another way in which heterogeneity can come into the picture. And finally, even if all the clients do the same number of local updates, they might use different local optimizers or local hyperparameters. So some clients might use a different learning rate or different momentum value, or they might even use something like adaptive local optimizers such as AdaGrad or Adam. And these aspects, these heterogeneous parameters across the clients can also lead to the local progress being asymmetric. So it turns out that although this heterogeneity exists in practice, most current implementation disregard it when we are aggregating the client's updates. So you just aggregate the client's updates in the proportion of their data set sizes without taking into account the fact that some clients have done more local progress than others. But it turns out that this heterogeneous local progress can be pretty bad, and it can actually cause inconsistency in the objective, which means that we end up optimizing the wrong objective function and not the true global objective that we set out to minimize. So to illustrate that, let me compare two cases, one with in the homogeneous setting where each client does the same number of local updates. So if, again, we have this toy example with two clients and each client does 2 local updates, then their averaged global model will move like this. And if you continue this with small enough tau and small enough learning rate, we can show that this global model will converge close to the global optimum X star. But on the other hand, if we consider a heterogeneous setting where, let's say, the first client does many more local updates than the second client, then by naively using the federated averaging algorithm, we will end up with a global model that is skewed towards the first client. And if in every communication round, the same thing happens, that the first client does more local updates, then this global model will continue to be skewed towards that client. And this kind of bias cannot be fixed by the techniques that are used to tackle data heterogeneity, such as using a small learning rate or using proximal methods, etc. It can be reduced, but it cannot be completely fixed. So in our work, in order to understand what solution this heterogeneous setting is converging to, we came up with a generalized version of the federated averaging algorithm. And in this generalized version, we were able to show that the homogeneous setting is minimizing or optimizing the true global objective. Whereas in this heterogeneous setting, we end up minimizing a mismatched global objective, which we denote by F tilde. And this global objective has a different weight that is assigned to the ith objective function, where this weight depends on the number of local updates that are done at that client. And depending upon the number of local updates, it can be arbitrarily different from the true global objective. In fact, it is matching with the true objective only in the case where all the tau i's are equal, which is the homogeneous setting. So to put it more concretely, in this generalized version of the federated averaging algorithm, we propose the following two ways of modifying the update rule. So this is the original federated averaging update rule, where each client does some local updates and the total accumulated update is denoted by delta I, where delta I is the summation of all of these local gradient steps scaled by the learning rate. And then we average all these accumulated updates in proportion of the dataset size. So we generalize this update rule in two ways. The first generalization is that we consider that this accumulated update, instead of just being a sum of the local gradients, it is a linear combination of the local gradients, where you can choose these weights AIK that are assigned to each of these gradients to be any arbitrary weights. Okay. So the nice thing about this generalization is that by choosing different values of AI, we can capture different local optimizers. So for example, the vanilla SGD setting would correspond to all the AIs being equal to each other. Some other algorithms, such as proximal methods like FedProx, would correspond to AI being like this, where you give a smaller weight to older updates and higher weight to more recent updates. Even momentum SGD, when used locally, can be captured by setting AI in this way. So by allowing these linear combinations of local gradients, we can subsume many different local optimizers. So that's the first generalization. The second generalization is that now the central server, instead of taking a weighted average of just these delta i's, it takes a weighted average of normalized local changes. So this delta I is now the accumulated update, where we have this linear combination of the gradients. We normalize it by the L1 norm of AI to change it to DI. So this is just a scaling factor. It doesn't affect the process that much. So each client will compute this accumulated local update, just normalize it by the scaling factor and send it to the central server. But now the central server is allowed to use any weight. Instead of PI, we allow it to use any arbitrary weight WI for the ith client's normalized gradient. So putting these two generalizations together, here is the update rule that we propose. So the update rule has three key elements. The first thing is the normalized update, which or the normalized gradient, which is determined by the choice of the local client side optimizer. It takes some linear combination of the local gradients and normalizes them. So for example, if you have this sequence of the local updates and the accumulated update is this blue color dotted arrow, then the normalized gradient would be like this green arrow, which scales down this dotted blue color arrow. Now, the second element are these aggregation weights, which are used to average these green colored normalized gradients at the clients. So these aggregation weights determine the direction of the global update, which we denote by this orange color arrow. And finally, the third aspect is this tau effective, which we call the effective steps per round. This decides the magnitude of the global update or the magnitude of this orange color arrow. So by setting different values of these parameters, we can change the algorithm, and we can show that this algorithm optimizes a surrogate objective, which is this weighted combination of the local objectives in proportion of WI. So there are several special cases of this generalized update rule. I'll just show one special case, which is the vanilla federated averaging framework, where these AIs will just become 1 over tau I. And the aggregation weights are equal to pi tau I divided by the summation of pi tau I. So here, the clients with more local updates will get a higher weight. Note that the reason that we have tau I here is because this weight is assigned to the normalized gradient. Because we are normalizing each gradient by tau I, we correct for that and add a tau I here in the numerator. And finally, the effective steps per round for vanilla federated averaging is just equal to the average of the number of local updates at each of the clients. So as we showed before, this algorithm minimizes a mismatched surrogate objective, which sets the weights in this way. So this perspective of coming up with the generalized update rule and coming up with the surrogate objective function for this generalized update rule actually directly gives us the solution to our inconsistency problem. So we can see that the problem is coming from these aggregation weights not being equal to pi. So what FEDNOVA, our proposed algorithm, simply does is that it changes these weights assigned to the normalized updates to pi. So what FEDNOVA does, illustrating that more concretely, instead of the federated averaging algorithm where you average these local accumulated updates, it's going to take the local accumulated update and scale it down by a factor of tau I. If a client does tau I local updates, it's scaled down by that many local updates. So you get these normalized gradients shown in green, and then it averages those normalized gradients instead of the accumulated local updates. So the FEDNOVA update rule is like this, and it optimizes the correct global objective function. So you might think that aren't we slowing down these fast clients because they are doing more local updates and now you're scaling it down by tau I? So that's a valid concern, but in fact, we can show that we can overcome that slowdown by choosing an appropriate tau effective or this global scaling factor such that the overall convergence is not affected. You can choose tau effective appropriately to ensure that the overall convergence is still as fast as federated averaging. So more formally, the convergence analysis of this generalized federated averaging framework shows that if we decay learning rate like this, then there are two terms in the error. The first term is a vanishing error term, similar to what we have in standard federated averaging. But now we also have this non-vanishing error term that is 0 only if there's no data heterogeneity or only if there's no computational heterogeneity, that is, we set these WIs to equal to PI. So this general analysis also provides insights into the convergence of several existing works like FedProcs and other algorithms that are subsumed within this FEDNOVA framework. Right. So next, let me just quickly show you the experimental results. So these are results on synthetic data. There are more results on other data sets in the paper. So the first thing that we observe here is that federated averaging, it can converge to a pretty high error floor. And FEDNOVA, by just correcting the aggregation weights, it's able to achieve much faster convergence to a lower error floor. Since FEDNOVA works with a whole class of local optimizers, it can actually be used in conjunction with vanilla local updates or momentum local SGD or proximal local updates, or even variance reduction methods such as scaffold and VRL SGD, etc. So instead of the standard federated averaging aggregation, we just change the aggregation weights. And by doing that small change, we are able to get up to a 10% accuracy improvement using this FEDNOVA framework. So finally, I want to just add a couple of slides here on talking about adaptive local optimizers. So I only focused on having the number of local updates being different at different clients. But as I mentioned before, even if the number of local updates are the same, what if the different clients use different local optimizers? So in particular, we can also get computational heterogeneity due to adaptive local optimizers. So although most current federated learning implementations use vanilla SGD as the local optimizers, it is well known that using adaptive optimizers like AdaGrad and Adam can give faster convergence in the single node settings. But in the federated learning context, these have all mostly been proposed only on the server side, not on the client side. So at the server side, when it aggregates the updates and changes the local models, some previous works have proposed using adaptive optimizers at that step. But it turns out that if you do local adaptive optimizers, we can get faster convergence as well. But the problem is that local adaptive optimizers will depend on local Hessians, which are heterogeneous across the clients. So this can lead to inconsistency similar to the computational heterogeneity objective inconsistency that I mentioned earlier. So to illustrate that, if we use just vanilla federated averaging, then we'll get something like this. This is for a simple quadratic objective function. If we use client-side AdaGrad, then we get really fast convergence, like this sharp drop at the beginning, but it converges to an inconsistent solution, so you'll get a much higher error flow. So in our recent work, we fix this solution bias that is coming from the local adaptation and heterogeneity and come up with this corrected version of local adaptive optimizers that gives a consistent solution and much faster convergence. So we cannot directly use the FEDNOVA framework to do this because the FEDNOVA framework works only when the accumulated update is a linear combination of the local gradients. Whereas in adaptive methods, this accumulated local updates is where you have some preconditioning matrix, AI, K, that's multiplying each local gradient, and then you're averaging these over the local updates. So it's a more complicated accumulation process where each element of the gradient vector is weighed differently. So to account for these adaptive methods, in our recent work, we came up with a way of correcting these generalized accumulated local updates by setting the normalized gradients like this, where there is a local correction term that is applied at each client. So this is a matrix that it multiplies with the result of its local adaptive optimizer. And then on the server side, there is a global correction where we also multiply this global matrix in order to make sure that the global objective is consistent with what we wish to minimize. So I won't show the details of the results here, but this is just a brief overview that we can also consider adaptive optimizers in this setting. Are there any questions on this part of the talk? I can pause here again.
Yes, we have a question by Konstantin.
Mm-hmm.
I'm just unmute him. So please go ahead, Konstantin. You're unmuted, Konstantin. We can't hear you. So maybe if you have a question, please type it to the chat and then I can read it out for you. So maybe in the meantime, I would also have one question. Mm-hmm. So with FEDNOVA, can you guarantee that if every device would run just tau min, where it's a minimum amount of step size on the clients, and then you would average that, comparing to actually what you the aggregation step that you do, that FEDNOVA is better than that?
Okay, that's a really good question. So what you're asking is that instead of allowing clients to do different numbers of local updates, what if we just set tau I as the minimum of all the tau I's? So we go by the slowest client, right?
Exactly.
So that it will give a consistent solution because the updates become homogeneous, but then it does slow down conversions because the number of effective local steps that you do per round reduces. So in the slides that I showed, there was this parameter tau bar or tau effective, which captures the number of effective local steps. And by using the algorithm that you proposed, that will reduce to the minimum of all the tau I's. Whereas in FEDNOVA, because we allow tau effective to be chosen freely, you can get faster conversions by doing more effective steps per round.
So if I get it correctly, this tau effective is some kind of a weighted average over those local taus, or weight based on the weight that it has in the like overall summation. So
yeah.
So another question is, what happens actually if you allow one specific tau to go to infinity? Because then this tau effective should also go to infinity. So does it admit to
sorry,
happen
I
in
think
FEDNOVA?
your audio got cut off. One specific client does what?
So what if you allow one tau to go to infinity?
Okay. So in the version that I presented, the tau effective is set to be equal to the average of the local taus, but tau effective is actually a hyperparameter. So you can think of it like a global learning rate that can be chosen freely.
Okay.
So we'll choose it to be some finite value.
So, but then, like, is it like when you allow this tau to go to infinity, does it mean that that client will converge to its local optimal solution?
Yes, so that client will converge to its local optimum solution, but then the global optimum will be pulled, like you will reduce the weight to that client. So infinity is a bit tricky because when we normalize the update, we are going to divide by tau I, right? So in the global model, then that client will just get zero weight because tau I is infinity and you're dividing its local update by infinity.
Thank you. Yes, then Konstantin just posted this question to the chat, and the question is, does FEDNOVA provide formula to compute alpha I optimality?
Alpha I did not get what you mean. Could you clarify?
So I also don't know what the alpha I stands for. So he says we saw a reduction to FEDPROX and SGD, but do you have specific formula to compute alpha i's based on, I guess
Oh, I
this
see.
is li's and mu i's.
I think, oh, I see. I think I get which alpha you're talking about. So in FEDPROX, when you add that proximal term, there is some mu parameter there. So alpha, which I've written on the slides, is proportional to mu. So that's a hyperparameter that is chosen in FEDPROX. And we can analyze the convergence of FEDPROX by incorporating that into the AI vector, which is used to get the linear combination of updates.
Thank you.
So alpha is actually proportional to a hyperparameter that is set in these proximal methods.
So yeah, there are no other questions in chat, no raised hand. So please continue.
Okay, thank you for the questions. So I think I don't have a lot of time, but the rest of the talk is also small. So I believe I should be able to cover it during the remaining few minutes. So in the last part of the talk, I want to talk about another way in which computational heterogeneity comes in federated learning, which is in the context of intermittent client availability. So as I mentioned before, only a subset of the clients will participate in each round. But here we want to understand, how do we choose that subset? If we have options among the set of available clients, can we choose them smartly in order to get better conversions? So to recall, for client selection in federated learning, what we do is that in every round, we select some subset of the clients, and only these clients will do the local updates, and their local updates will be average at the server. So effectively, what we are doing is we are optimizing a surrogate objective F tilde that only depends on the selected subset of clients. So in order to ensure that this surrogate objective is consistent with the global objective, in most current works, the client selection is done in an unbiased manner, where you sample clients with probability pk with replacement, or you sample them uniformly, but weigh them. When you take an average of their updates, you weigh it by pi. So by doing this, we can ensure that the expected value of F tilde, the surrogate objective in each round, is equal to the global objective f of x. So most works in federated learning, when they talk about partial client participation, they consider these unbiased selection schemes. And many prior results which are derived for the full client participation setting can be extended to these unbiased client selection schemes. So in fact, the FEDNOVA framework can also be extended to to partial client participation with unbiased client selection. But in this work, we wanted to understand what happens if we choose clients in a biased way. So to illustrate that, let's look at a toy example with two clients. If I do unbiased client selection, and these are the two objective functions. So the blue color objective function is for the first client, the green color is for the second client, and the global objective, which is shown in red, is the average of these. So if we start off at some arbitrary point and choose one of the clients at random in every round, then let's say if we choose the second client, then we move along the second objective function. Now in the next round, again, we choose the second client, so we move along the second client's objective function. In the third round, maybe we choose the first client. So now we switch to the blue curve and move along this objective function. So in such a way, it can switch back and forth between the two local objectives. And depending upon the sequence, it might end up where it started, like here. So although in expectation, we will eventually get to to the stationary point of the global objective, it might take longer to get there. Instead, if we use something like a biased client selection process where in every round, we choose the client which has a higher value of local loss. So starting from here, because client 2 has higher local loss, we keep on selecting that. And only when client 1's local loss becomes larger, we switch to that client. So we can see that here in just 5 iterations, we were able to converge close to the global minima, whereas here we could get stuck in some loop. So this intuitively shows that biased client selection towards choosing higher loss clients could give faster conversions. But on the other hand, too much selection skew could potentially give a solution bias because you're only choosing clients which have high local losses. So some other clients which have low local losses might get ignored. So to understand, we came up with a metric called the selection skew, which measures how much a policy, a selection strategy is biased towards higher loss clients versus lower loss clients. So this is the formula, but all you need to know is that this selection skew metric rho is 1 if our client selection is unbiased, and it is greater than 1 if the bias is towards clients with higher loss, whereas it's less than 1 if the bias is towards clients with lower loss. And with this selection skew, we can show that the conversions can actually speed up in terms of rho. So if you have a larger value of selection skew rho, you get this factor in the denominator of the first term, so it converges faster. But then the bias in the solution can increase with the selection skew, and it can also increase with the amount of data heterogeneity. So when we introduce bias in the client selection, we have to do that carefully such that it's not too much bias. And to strike a good balance between these two terms, we came up with a selection strategy or framework called the power of choice client selection framework. So this is inspired by power of D load balancing, which is done in the context of multi-server systems. It is also similar to some importance sampling based approaches that have been proposed for SGD. So the main idea is that in every round, you can sample some candidate set of clients, and then these clients will send estimates of their local losses to the central server. And by just comparing these estimates of the local losses, we then select the M clients with the largest local losses. So here you can see that the size of this candidate set D can affect the selection skew. By setting D equal to M, we just get unbiased client selection. Whereas if we increase the value of M, increase the value of D, you get bias more and more towards high loss clients. So this is also connected to importance sampling techniques in single node SGD setting, like I mentioned before. And we also have some more efficient variants of this method where step 2, which is where we compute estimates of the local losses, can be either completely skipped or it can be made more communication and computation efficient. So it turns out that these power of D selection strategies give pretty good performance. They give faster conversions in many of the experiments that we ran. Increasing the value of D gives faster conversions, but it might increase the solution bias. So we could also come up with an adaptive version of this method where this is called it's not shown here, but we could also come up with an adaptive version of the method where D changes during the training process so that we get fast conversions at the beginning, but we also get low solution bias at the end. And our experiment showed that if you have more data heterogeneity, then these kind of bias selection strategies help even more to get better accuracy. So that was a short summary of the intermittent client availability portion. I think I'll wrap up at this point to leave some time for questions. So to conclude, the federated learning framework poses many interesting and unique challenges. In this talk, we focused on computational heterogeneity and intermittent client availability, but there are many other challenges that have been considered in several recent works and many ongoing works as well. So finally, here are the archive links to the papers that were covered in this talk and some other papers that are on distributed SGD that are also relevant. So thank you again for your attention. I am happy to take any questions.
Thank you for your excellent talk, Gauri. So if there's a question, please just raise hand or post your question to the chat. So there are 2 questions in the chat. I'll try to unmute first, Konstantin. Maybe this time it's going to work. Or maybe it's not. So I can just read out loud the question. Yeah. So Konstantin saying, thanks for the talk. So FEDNOVA is presented in FedML AI benchmarking framework. And he's curious whether your group is putting some work in this benchmarking framework.
Oh, okay. That's a good question. I think my student Jianyu Wang would be a better person to answer the question. I think he's in communication with the people who are leading the development of that framework. And I don't know what's the current status of being integrated into it.
So then we have a question from Trapti who asked, which dataset and framework would you suggest for a hands-on experience in federated learning? I guess that's more like a general question or recommendation.
Okay. I think that is something that would benefit the whole community, actually having a good common benchmark framework to analyze and evaluate federated learning algorithms. Something that we have found to be easy and accessible to start with is using a synthetic data set and using the Dirichlet allocation scheme to split up the data set across different clients in a heterogeneous manner. So that is a good sanity check method to start with. And then going forward, you could consider other data sets as well.
Then there is another question from Vincent, and he thanks you for the talk. And the question is whether you can remind us the paper in which this kappa assumption is described.
So the kappa assumption is described in this paper, the tackling objective inconsistency problem, which was last year in URIPS.
So any other question or comment? Yeah, so we are a bit over time. Okay, now we have one question by Steve, so I can try to unmute him. You can ask the question. So please go ahead, Steve.
Yes, thank you, Samuel. Hi, thanks for the talk, Gauri. I was wondering, if you have any insights on the interaction of FEDNOVA with the fidelity of the updates coming from the client. So, for example, if you integrate differential privacy in the whole process of federated learning, how does this interact with taking equal steps towards the updates?
Okay. That's a really good question. So I think actually the privacy aspects of doing heterogeneous local updates would be really good to look at. If you don't do this correction that we are proposing in FEDNOVA, then there might be some privacy issues, because clients, if they do more local updates, then they might reveal more information about their local models. So in fact, I believe that doing this correction will improve the privacy, but that's just an intuitive, like, first level guess that I have. You could use, so naively, you could use differential privacy techniques on top of this. So on the normalized local gradients, you can add noise, as is done in differential privacy. If you want to do local differential privacy, or if you want to do global differential privacy, you could add noise to the aggregated update. But I don't have any insights in terms of the conversions or privacy guarantees yet.
Okay, great. Thanks.
Any other question? Okay, so it seems that we have no other questions. So thank you again, Gauri, for your excellent talk. And
thank you again for the invitation and for moderating the questions. It was a pleasure talking, and thank you for your attention.
Yeah, so thank you for tuning in today, and hopefully see you all next week. Bye-bye.
Bye, thanks.